Now we are going into the details of dynamic programming algorithm design strategy. Basically, there are four sequence of steps in a dynamic programming algorithm. The first step is characterize the structure of an optimal solution. Then second step is recursively define the value of an optimal solution. Then compute the value of an optimal solution in a bottom-up fashion. Then construct an optimal solution from computed information. So the initial step is that we should actually characterize the structure of the optimal solution. Then actually characterize the structure of an optimal solution. That's why we are saying it's a structure of an optimal solution, which means you can have multiple optimal solutions also. That we have seen in the case of minimum cost spanning trees. You can have multiple minimum cost spanning trees. That's why you are saying that you must first characterize the structure of an optimal solution. So how the optimal solution will look like. So that structure you should specify. Second step is that you should recursively define the value of an optimal solution. Okay, so you can actually the value of an optimal solution is actually defined recursively in terms of values of its subproblems. Okay, so that's why we are recursively define value of an optimal solution. That is actually we are defining the value and compute value of an optimal solution in a bottom-up fashion. So what happens, we'll compute the value of an optimal solution in a bottom-up fashion. So which means we'll compute the smallest subproblem or solution for the smallest subproblem first, then we'll record it, then the next smallest subproblem, etc. So then we will combine these two subproblems to get the next level subproblem, etc. So that's what computing the value of an optimal solution in a bottom-up fashion. So finally we will reach at the top where we get solution of the original problem. Okay. Then construct optimal solution from computed information. So final solution will be computed from all this computer information. Okay. So computing, we are initially computing value of these optimal solutions, and they will be stored in some place in some tables, and the final solution will be computed from all this computer information. Okay. So the first algorithm that we are going to see today is under dynamic programming is matrix chain multiplication. So again, matrix chain multiplication is actually we are given a sequence, that is a chain a1, a2, etc. an of n matrices to be multiplied. Okay, and we wish to compute the product a1, a2, etc. an. So that is the input. You have a chain of matrices and you need to multiply these matrices. And you can evaluate the product, this product, that is a1, a2, etc. an, using some standard algorithm for multiplying pairs of matrices. So we know the standard algorithm for multiplying pairs of matrices. Even though we have n matrices here, we'll compute pair of matrices. So these n matrices will be divided, will be broken down into some pair of matrices. So that we will compute this product of these pairs. Okay, and how we'll find out these pairs? So we will find out this pairs by using some parenthesizations. Okay, so suppose we find out one pair, we will parenthesize them. So which means these two will be multiplied first, and we will use one more parenthesis with another matrix. So which means after computing these first two matrices, we will multiply that result with the third matrix, etc. So that is the speciality of parenthesizations. So a product of matrices is fully parenthesized if it is either a single matrix or the product of two fully parenthesized matrix products surrounded by parentheses. So which means and again matrix multiplication is associative. So all parenthesizations yield the same product. So for example, if the chain of matrices is a1, a2, a3, a4, we are taking 4 matrices. and the product will be A1, A2, A3, A4, and this can be fully parenthesized in 5 distinct ways. The first method is A1, A2, then A3, A4. So here A3, A4 will be computed first, and their product will be multiplied with A2, or A2 is multiplied with the product of A3 and A4. Then A1 will be multiplied with the product of this thing. That is one parenthesization. Then next one is A1, then A2, A3. So A2, A3 is within one parenthesis. So which means A2, A3 will be computed first, and this will be multiplied with A4. And finally A1 will be multiplied with this product. Then third parenthesization is A1, A2 will be multiplied first, then A3, A4 second, then their products will be multiplied finally. Or you can multiply A2, A3 first, then A1 and this product, then finally the product with A4. Or A1, A2 will be multiplied first, then A3, and finally A4. So these are possible parenthesizations for this A1, A2, A3, A4 chain. So let us again look at this matrix multiplication algorithm. So we know these concepts, we know this algorithm, and what is time complexity of this algorithm? It is actually, we know that if it is a square matrix, then the time complexity is big of NQ. Okay, suppose it is not a square matrix, then what will be the time complexity? Suppose we have two matrices A and B. So A with dimension P by Q and B with Q by R. We know that the time will be P into Q into R. That is given here for I is equal to 1 to rows of A, for J is equal to 1 to columns of B. We are setting this value, then K is equal to 1 to columns of A. So that is the basic thing. P and this values are, this is Q. So the time will be big of P, Q, R, where P is number of rows of A, Q is number of columns of A, and R is number of columns of B. So time complexity for this matrix will be big of P, Q, R. So what is meant by that? We are always telling this time complexity as number of, this is as big of P into Q into R. So that actually matters when we are interested in this number of scalar multiplications that we perform, that we are going to perform. So for example, to illustrate different costs incurred by different parenthesizations of a matrix product, consider the problem of a chain A1, A2, A3 of 3 matrices. So suppose we have 3 matrices A1, A2, A3. So the dimensions are for A 10 by 100, A2 100 by 5, A3 5 by 50. So if we multiply these matrices using the parenthesization A1, A2, A3. So we will multiply A1, A2 first, and that product will be multiplied with A3. So what is the time complexity, or how many multiplications are required in this case? Okay. So 10 by 100. So first matrix is 10 by 100, second is 100 by 5. Time will be big of P, Q, R. So that is nothing but 10 into 100 into 5. So which means 5000 scalar multiplications to compute a 10 by 5 matrix product A1, A2. So what is A1, A2? A1, A2 will be its dimension 10 by 5. Okay. And you need 5000 scalar multiplications for computing this product. and plus another multiplication, that is this A1 A2 product of this A1 A2 will be multiplied with A3, and your A1 A2 matrix product A1 A2 is actually a 10 by 5 matrix, and that is multiplied with 5 by 50. So, the total multiplications for computing the second product is actually 10 into 5 into 50, that is 2500 scalar multiplications. Okay. So, which means a total of 7500 scalar multiplications if you parenthesize it in this manner. So, instead of this, suppose we multiply using another parenthesization, that is A1 and A2 A3. We perform. So, first step is A2 A3, product of A2 A3. Okay. A2 is 100 by 5, A3 is 5 by 50. So, number of scalar multiplications will be 10 into 5 into 50, that is 25,000 scalar multiplications for getting this 100 by 50, 100 by 50 product A2 A3, and plus another one, then this A1 should be multiplied with this. So, 10 by 100 and 100 by 50. So, which means 10 into 100 into 50, that is equal to 50,000 scalar multiplications to multiply A1 by this matrix. Okay. So, which means a total of 75,000 scalar multiplications. So, if you choose this order, that is A1, A2, A3. So, A2, A3 will be computed first, then A1 is multiplied with A2, A3. If that is the order, then you need 75,000 scalar multiplications. But if you choose A1, A2, then with A3, then you need just 7500 scalar multiplications. So, second order means that actually the first one is actually 10 times faster than the second. So, a matrix chain multiplication problem can be stated as follows. Given a chain A1, A2, etc. an of n matrices where I is equal to 1 to n, matrix AI has dimension Pi minus 1 by Pi. So, each AI has dimension Pi minus 1 by Pi. Then fully parenthesize the product A1, A2, etc. an in a way that minimizes the number of scalar multiplications. So, in a matrix chain multiplication problem, actually we are not multiplying the matrices. So, we are finding out an order for this multiplication. We have n number of matrices with us. So, we will try to find out an order of this multiplication. Okay. So, this we will find out, we will actually take all possible multiplications and we will choose a multiplication which has the minimum number of scalar multiplications. Okay. So, that is why you can use or you can go for a dynamic programming